Ever wondered how Amish blacksmiths create tools lasting 50 to 100 years when modern store tools fail within 5? It's high carbon steel at 1% carbon, individual heat treatment at 1450 degrees, and 8 hours of handwork per tool. This is metallurgy modern manufacturing abandoned for profit. The forge setup. The Amish blacksmith shop is built around the forge, the heat source, transforming cold steel into workable material, and the anvil providing the surface where hammerwork shapes heated metal into functional tools. The coal or propane forge reaches working temperatures of 2,500 to 3,000 degrees Fahrenheit, hot enough to make steel glow bright orange to yellow and become plastic enough for shaping. Coal forges are traditional and preferred by most Amish smiths because coal burns hotter and longer than propane, costs less per BTU, and provides the reducing atmosphere that prevents excessive oxidation of heated steel. A coal forge consumes 20 to 30 pounds of coal daily during active work, costing $3 to $5 daily or $60 to $100 monthly. The bellows or blower forces air through the fire, increasing combustion intensity and temperature. Traditional hand-cranked bellows require an assistant, often a son or apprentice, turning the crank continuously while the smith works, providing coordinated teamwork that has characterized blacksmithing for centuries. Electric blowers used in some shops eliminate this need, but still require constant attention managing airflow to maintain precise temperature. The anvil is the smith's primary work surface, a solid steel block weighing 150 to 400 pounds, providing the mass necessary to absorb hammer blows without bouncing. The anvil must be heavier than the work being done to prevent energy loss. A light anvil flexes and bounces, wasting hammer energy and reducing forming efficiency. The flat face provides surface for general hammering. The horn, the tapered projection, allows bending curves. The hardy hole accepts various tools inserted for specialized operations. The basic tools: hammers weighing 2 to 6 pounds, tongs for holding hot steel, hardies for cutting, and swages for shaping cost $3,000 to $8,000 for a complete professional setup. This compares to factory equipment costing $2 to $10 million, yet the simple setup produces superior tools through skill substituting for mechanical precision. Steel selection. The material difference between Amish forged tools and modern store tools begins with steel selection. High carbon steel containing 0.8 to 1.05% carbon versus the low carbon steel at 0.18% used in cheap mass-produced tools. The carbon content in steel determines its hardness potential, edge retention, and overall performance. High carbon steel with 0.8 to 1.05% carbon can be hardened through heat treatment to Rockwell 58 to 62 HRC, hard enough to hold a sharp edge through hundreds of hours of use. Low carbon steel at 0.18% cannot be hardened effectively regardless of heat treatment, reaching only Rockwell 25 to 30 HRC soft enough that edges dull within hours of use. The specific steel grades Amish smiths use include 1084 and 1095 tool steels for agricultural implements, 1 tool steel for chisels and cutting tools, and 5160 spring steel for tools requiring flexibility combined with toughness. Each grade has specific working temperature ranges, quench media requirements, and tempering temperatures that the smith must know precisely. This material knowledge is transmitted through apprenticeship over years. No reference books, just memorized knowledge applied through experience. The steel cost is $3 to $8 per pound for quality high-carbon tool steel, compared to 50 cents to $1 per pound for the mild low-carbon steel factories use. A hoe head requiring 1 pound of steel costs $3 to $8 in material alone. The factory hoe uses 50 cents to $1 in steel. This 5 to 8 times material cost difference is real, but represents only a fraction of why Amish tools cost more. The labor investment dwarfs the material cost difference. Heating process. The heating process requires reading fire color to judge steel temperature precisely, a skill taking years to develop but critical for every subsequent operation, because steel worked at wrong temperature produces inferior results. regardless of technique. The color progression tells the experienced smith exactly what temperature the steel has reached. Black steel is cold, below 400 degrees. Dark red appears around 800 degrees too cold for most work. Bright red at 1000 to 1100 degrees allows bending but not efficient hammering. Orange at 1200 to 1300 degrees is the minimum for general forging. Bright orange to yellow at 2100 to 2300 degrees is the ideal working range for most operations. White heat at 2300 plus degrees is maximum temperature before steel begins burning and losing carbon. The working window is brutally short. Steel at optimal forging temperature of 2100 to 2300 degrees cools to the minimum workable temperature of around 1800 degrees in 30 to 60 seconds. The smith must complete his planned hammerwork within this window before returning the piece to the forge for reheating. A complex tool requires 8 to 15 reheating cycles, each followed by 30 to 60 seconds of focused hammerwork, advancing the piece toward its final shape. The total heating time for a single tool is 30 to 120 minutes of fire time spread across those 8 to 15 heats. The smith uses waiting time productively, filing a finished piece, preparing the next piece, sharpening tools, or training an apprentice. But the forge's rhythm dictates the work pace in ways modern production cannot replicate. Hammer work. The hammering transforms heated steel from raw bar stock into tool shape through a series of techniques, each producing specific changes in the steel's form, drawing out for length, upsetting for mass concentration, bending for curves, and punching for holes. Drawing out lengthens and thins steel by hammering across its width while the piece is supported on the anvil face. Each hammer blow displaces steel sideways and downward, thinning the cross-section and extending the length. A hoe blade starts as a thick bar and is drawn out to thin flat plate through dozens of overlapping hammer blows progressing from one end to the other, each blow precisely placed to create even thickness throughout. Upsetting concentrates mass by hammering on the end of the piece, compressing it shorter and thicker. This technique is used when a tool needs extra material in a specific location, creating the eye of an axe head where the handle inserts, or thickening the cutting-edge zone before final shaping and grinding. The piece is held vertically with the end on the anvil and struck from above, or held horizontally and struck on the end. The total hammer blow count per tool reaches 200 to 500 individual strikes. Each blow delivers 15 to 25 pounds of force, meaning 3,000 to 12,500 pounds of cumulative force shapes each tool. The precision required is extraordinary. Hammer blows misplaced by 1/4 inch can create lumps requiring correction or thin spots requiring additional heating and work to fill. The grain alignment benefit of hand forging over casting or machining is real and significant. Hammer blows compress and align the steel's crystalline grain structure, creating directional strength that follows the tool's stress lines. A forged axe head has grain running parallel to the cutting edge, providing maximum resistance to the splitting forces experienced during use. A cast axe head has random grain orientation with no directional strength advantage. Edge geometry. The cutting-edge geometry determines how well a tool performs its specific function. Each tool type requires different bevel angles optimized for the forces and materials encountered during use. The hoe blade requires a 25 to 30 degree bevel angle steep enough to provide strength, preventing the thin edge from folding under the lateral forces of soil cultivation, but shallow enough to slice through soil with reasonable effort. The blacksmith files this bevel by hand, checking the angle with a protractor or practiced eye, working until the bevel is consistent from one end to the other. The axe head uses a 20 to 25 degree compound bevel, a primary bevel at 20 degrees for sharpness, combined with a secondary micro bevel at 25 degrees, providing durability at the very edge. The compound geometry allows sharpness for initial wood fiber cutting while maintaining edge stability, preventing chipping when the axe encounters knots or grain reversals in wood. The chisel requires 25 to 35 degrees depending on the material. It will cut softer degrees for wood chisels that need razor sharpness steeper degrees for metal cutting chisels that need impact resistance. The draw knife uses a single bevel at 15 to 20 degrees for maximum sharpness in the pulling cuts characteristic of shaving wood. Modern factory tools are stamped or ground to nominal angles that often deviate 5 to 10 degrees from specifications due to the speed of production. This deviation seems minor but significantly affects performance. A hoe ground to 35 instead of 27 degrees requires 30% more force to penetrate soil, tiring the user faster and reducing daily work output substantially. Heat treatment. The heat treatment process hardening, followed by tempering, transforms properly shaped high-carbon steel into a functional cutting tool with the hardness to hold an edge and the toughness to resist breaking under impact. The hardening begins by heating the shaped tool to 1450 to 1500 degrees Fahrenheit, the critical temperature where steel's crystal structure transforms from ferrite to austenite, allowing carbon atoms to move freely through the iron matrix. The smith judges this temperature by the steel's color, and by holding a magnet near the piece, steel loses its magnetic attraction at exactly the critical temperature, providing a non-contact thermometer requiring no instruments. The quenching plunges the heated tool into oil, typically vegetable oil or commercial quenching oil at room temperature. The rapid cooling locks the dissolved carbon in place, creating martensite, the hard, brittle crystal structure that gives high-carbon steel its cutting ability. The oil quench cools steel faster than air but slower than water, providing hardness without the cracking risk that water quenching creates in complex shapes with varying cross-sections. The hardened steel is extremely hard but equally brittle. It would shatter rather than bend under impact, making the tool unusable despite its hardness. Tempering reduces this brittleness by reheating the hardened tool to 375 to 450 degrees Fahrenheit. The smith uses a propane torch or places the tool on the edge of the forge fire, watching the oxide colors that appear on the polished steel surface as temperature rises pale yellow at 400 degrees, straw yellow at 430 degrees, brown at 460 degrees, and blue at 500 degrees. The target for most tools is the straw yellow color, indicating 375 to 425 degrees. The individual attention during heat treatment creates consistency impossible in factory batch processing. The factory loads hundreds of tools into furnaces, setting temperature controllers and hoping every piece reaches the same temperature uniformly. The Amish smith treats each tool individually, adjusting the process based on the specific piece's size, shape, and steel response. The factory failure rate for improperly hardened tools reaches 15 to 25%. The Amish smith's failure rate is under 5%. What stores can't sell? The categories of tools that modern stores literally cannot stock or sell represent the clearest argument for Amish blacksmithing's continuing relevance and irreplaceable value. The custom geometry tools cannot be mass-produced because they're specific to individual users or tasks. A left-handed farmer needs a hoe with reversed bevel angle that stores don't carry. A particularly tall farmer needs tools with longer handles that standard sizes don't provide. A specialty crop requires a weeding hoe with specific blade width and angle matching the crop row spacing exactly. The Amish blacksmith makes these tools to exact specifications, while factories cannot justify the production runs for small volume specialty items. The obsolete tool patterns that were standard a century ago but disappeared from mass production are available only from traditional smiths. The scorp, a curved draw knife for hollowing bowls and chair seats, hasn't been manufactured commercially for decades, but remains useful for traditional woodworking. The slick, a large paring chisel used for timber framing, disappeared from hardware stores when timber framing was replaced by dimensional lumber construction, but remains necessary for Amish barn builders. The travisher, the in-shave, the froe tools, essential for traditional crafts, but absent from modern retail. The repaired and modified tools represent another category stores cannot provide. An Amish farmer's grandfather's axe with a broken eye can be brought to the blacksmith, who welds, reshapes, and rehardens it, restoring full function. A plow blade worn thin can be built up with new steel welded and forged into the worn areas. Stores can only sell new tools. They cannot repair, modify, or restore existing tools with the metallurgical skill that preserves irreplaceable pieces. Cost reality. The price comparison between Amish forged and store-bought tools appears to favor store tools initially, but the life cycle cost analysis reverses this conclusion completely. The Amish hoe costs $45 to $85 versus $15 to $25 at hardware stores. The Amish axe costs $120 to $200 versus $30 to $60. The Amish draw knife costs $80 to $150 versus $25 to $45. The Amish chisel set costs $150 to $300 versus $40 to $80. The initial price difference of 2 to 4 times seems substantial until lifespan is considered. The Amish tool lasting 50 to 100 years with proper care costs $45 to $85 over that lifetime, less than $1 to $2 per year for a hoe used daily in the garden. The store tool lasting 5 to 10 years costs $15 to $25 per purchase, requiring 5 to 10 replacements over 50 years, totaling $75 to $250 more expensive than the Amish tool despite the lower initial price. The performance difference adds economic value beyond simple price. The Amish hoe with properly hardened high-carbon blade cuts through soil with 30 to 40% less effort than the soft store blade that bends rather than cuts. The reduced fatigue means more work accomplished in the same time, effectively multiplying the tool's productivity. The Amish blacksmith produces tools that modern stores cannot sell: custom geometries, obsolete patterns, repaired antiques, and properly heat-treated high-carbon steel tools, lasting 50 to 100 years through 4 to 8 hours of handwork per tool, applying metallurgical knowledge that modern manufacturing abandoned for speed and profit. Margins. The forge setup reaching 2,500 to 3,000 degrees, the high-carbon steel at 0.8 to 1.05% carbon, the 30 to 60-second working windows requiring 8 to 15 reheating cycles, the 200 to 500 hammer blows per tool, and the individual heat treatment achieving Rockwell 58 to 62 hardness, all combine, creating tools. The $45 to $85 price makes look expensive until the 50-year lifespan makes them the cheapest tools available per year of use.